Hello everyone, welcome to this class. This is Teacher Simon taking you through Cambridge International AS and A-Level Chemistry Paper 22 for Feb March 2021. Question 1. The rate of chemical reactions is affected by changes in temperature and pressure. Part A, Roman 1. Draw a curve on the axis to show the Boltzmann's distribution of energy of particles in a sample of gaseous krypton atoms at a given temperature. Label the curve T1 and label the axis. Okay, so the axis, of course, the vertical axis is for the number of particles. Number of particles. And then the horizontal axis, here we have particle energy, where we find the activation energy, that energy the particles need, the minimum they need to react. So I can say kinetic energy, I can say particle energy, or even just energy. Just energy is enough. Then from there to sketch, it's like a normal distribution curve. So we just do like this, something like that, then you curve it off. So that is that. Then Roman 2, this one they said we label it T1. So I will say this is T1. On the diagram in A Roman 2, draw a second curve to show the distribution of energies of the krypton atoms at higher temperature. So for higher temperature, we see this one here, the peak, going lower. And also in fact, let me change the color here, maybe to red. We see that this one actually bends to the right, so it will be, but then the peak will be lower, okay, than the previous one. So then we can go like that. So meaning at a given temperature, at a higher temperature, we are seeing many particles. Let's say this is the activation energy needed. So at higher temperature, we are seeing now very many particles that are added on to these ones that are able to react, because these are the ones that are supposed to have this kind of energy. The minimum has to be this activation energy and then more. So they increase, okay? And that is that. So we can label that one. Is it T2? Yes, we can label it T2. And then that is that. It has to bend to the right. Okay, you can even, for you when you're drawing, you can make this one dotted. Okay, as simple as that. Then next, the Boltzmann's distribution assumes that the particles behave as ideal gases. Roman 1, state two assumptions of the kinetic energy, the kinetic theory, as applied to ideal gases. Now, for an ideal gas, we should know that there are no van der Waals forces of attraction between the particles, okay? So I can say no forces of attraction, no forces. Even if you don't say van der Waals, no forces of attraction between the particles. So the particles are free to move, okay? And when we come to the liquids, there are significant forces of attraction between the particles. So that's why the particles are in layers and they are able to slide over each other. And then in solids, they are closely packed. That means the forces of attraction are really stronger compared to the gases. So for the gases, they are just distant from each other, the particles, so meaning the forces of attraction have to be negligible. Okay, and also these particles keep on knocking the walls of the container. Okay, they keep on colliding with the walls of the container, and there is no energy that is lost. So that means the collisions between the gas particles, between those gas particles and also the walls of the container are perfectly elastic. In elastic collision, that is when maybe they can stick together. Now that one causes a reaction, okay, but they don't stick, they just knock and then go away. So I will say collisions between gas particles and walls of the container are perfectly elastic. Okay, so that is that. Another one can be particles have negligible volume compared to the volume of the container. So when you place a gas in a container, it is going to occupy all of that space in there. So that is what you can also talk about, that particles have rigid spheres and many others. But since they asked for 2, so those are the ones that I'm going to give. Then Roman 2, 2 grams of krypton gas. This one is placed in a sealed 5 decimeter cubed container at 120 degrees C. Calculate the pressure in pascals of krypton gas in the container. Assume krypton gas behaves as an ideal gas. Of course, here, now we are going to use the ideal gas equation, which states that PV is equal to nRT. And N is the same as mass over the MR. Okay? Then times the RT here. Now, when I divide through by volume, it will come here. Okay? So, but in here, volume, okay, must be in meters cubed if pressure is in pascals or Newton per meter squared. Remember, pressure is force over area, okay? So this is newtons, and then this is meter squared. So that's why it is Newton per meter squared, okay? Then temperature has to be in kelvins. Temperature has to be in kelvins. Now, we know that 100 cubic centimeters, 100 centimeters, this one is equivalent to 1 meter. Now, how about if I cube this one, okay, 100 cubed, so centimeters cubed will be equivalent to 1 meter cubed. I'm trying to convert to meters cubed. So meaning this one here is actually the same as saying a million. 1,000, then 1,000 cubic centimeters is equivalent to 1 meter cubed. But 1,000 cubic centimeters is equivalent to 1 liter or 1 decimeter cubed. So that means here I will have 1,000 decimeter cubed, okay, is equivalent to 1 meter cubed. You see that? So that means when I'm converting from a decimeter, so 1 decimeter cubed will be equivalent to 1 over 1,000, okay, meters cubed. In other words, I will have 1 decimeter cubed is equivalent to 10 power negative 3 meters what? Cubed. Okay, this one is very, very important. If we were changing from, if we had our volume in meters cubed, okay, in centimeters cubed, then we would have multiplied, because this one you divide through, okay? So we would have multiplied by 10 to power negative what? 6. So what is the mass? The mass is given as 2. Then molar gas constant is 8.31. Then the temperature, remember, is 120. So I will add 273 to convert it to kelvins. And then the MR, or for this case, it is going to be the AR of krypton. So when you check the periodic table, the relative atomic mass of krypton is 83.8. Now the volume is 5 decimeters cubed, but remember, where there is decimeters cubed, we are going to substitute this one, okay? So we are going to multiply it by 10 to power negative 3 to be in meters cubed, okay? So all together here, what do we get? We have 2 times 8.31 times, this is 120 plus 273. Then down here we have 83.8 times 5 times 10 to power negative 3. So 15588.68735. 155 88.68735. Okay, so that is that. But to three significant figures, I can round this one here off to this, and then it becomes 1, 5, 6, then 0, and then 0. Okay, because these are 5 here. So that will be that, three significant figures. Roman 3, state and explain the conditions at which krypton behaves most likely as an ideal gas. Now, of course, here, since we are not supposed to have significant forces of attraction between the particles, then that means we must have low pressure. Okay, low pressure. Remember, when you increase the pressure, okay, you have, let's say, these particles here like that. Then when you increase the pressure, now you have many particles per unit what? Volume. So here they are close to one another. So the intermolecular forces of attraction become significant. You see that? So we must have low pressure and high temperature. And high temperature. Because remember, for high temperature, this one completely breaks down the intermolecular forces of attraction. As simple as that. So I would therefore say here in my explanation, they said state and explain the conditions. So this is because the volume of particles is negligible compared to the volume of the container. And also van der Waals forces are insignificant when you use these two here. Part C, krypton reacts with fluorine in the presence of ultraviolet light to make krypton difluoride. Okay, activation energy for this reaction is 385 kilojoules per mole, and the enthalpy change of formation of krypton difluoride is this one here. Roman 1, use this information to complete the reaction profile diagram for the formation of krypton difluoride. Label EA and DHF on the diagram. Okay, assume the reaction proceeds in one step. So since this one is an endothermic reaction, that means the reaction takes in energy. So whatever comes out of that comes out with very high energy. So that means I'm going to draw this. Of course, there is this hump here, which is for the activation energy. Then I can have the products here, which are far higher in energy compared to the reactants, because this one is an endothermic reaction. Okay, the enthalpy of formation here is positive. So I'll have the products here. So since here they wrote reactants, these are the ones that are actually supposed to be here. So I also don't need to put this one here. I will just put products. So products. And then one thing we need to know is that we shall put this dotted line here, and then we put this arrow here. Okay, and this one here represents the activation energy. Okay, so I'll just put EA here, just that, activation energy. And then the enthalpy change is positive, so I'll put an arrow here. It is in between the products and then the reactants, so I'll put DH. Okay, DHF, and that is that. Nothing else we need. Roman 2, explain in terms of activation energy, EA, and the collision particles how an increase in temperature affects the rate of a chemical reaction. How it affects. So first of all, the reaction rate increases. Okay, reaction rate increases. Now, when you increase the temperature, these particles are going to gain more energy. Okay, they are going to take in that energy, then they start moving faster. So, in moving faster, even their energy, remember, has increased. So, we are going to have many particles that have energy equal or greater than the activation energy. So in that case, we are now going to see the collisions becoming more frequent and successful, leading to a reaction. So we can say increase in temperature means more particles have energy greater or equal to the activation energy. Okay, so therefore, frequency of successful collisions increases. So for the rate, you have to talk about the frequency of successful collisions, you see? And for the temperature, since it increases the energy of the reactants, then you have to tell us about the activation energy. The energy they have, is it greater or equal to activation energy? If we are talking about the yield, then you talk about the position of equilibrium shifting to the side. That gives you the what? The yield. You see that? So that is that.